Look at the reactions of substituted benzenes as it pertains to electrophilic aromatic substitution. So previous video discussed the whys and the wherefores of electron donating and withdrawing groups as they pertain to ortho-para direction and whatnot. But here we can quickly just say that strong donating groups are ortho-para directors because they pi donate into the aromatic system with a lone pair next door. Moderate donators are ortho-para directors that donate next door with a lone pair, but they also have that lone pair split with a neighboring electronegative atom, so there's not a full resonance towards the ring. A weakly donating group only donates through hyperconjugation and includes the alkyls, aryls, alkenyls, and alkynyl groups, so the hydrocarbon groups that are attached to benzene. With our reference compound benzene, it will be unsubstituted as our reference point, and so the donators activate electrophilic aromatic substitution. What we're going to look at now as we move down, and again as we move down this chart, we're getting slower and slower for EAS reactions. So the moderate or the strong donators are the fastest, the strong withdrawers are the slowest. We're about to get there. Weakly withdrawing are the halogens. They withdraw due to their electronegativity in their sigma system, so they'll put a delta plus into the ring. Excuse me. And looking at our moderate withdrawing groups, they withdraw from the pi system up into their electronegative atom that is attached just next door to benzene. So again, the squiggly lines are indicating that a benzene's attached or some other group's attached. Here we're talking about benzenes though. So electrophilic substitution withdraws from the ring carbonyl first with these moderate withdrawers. The strong withdrawing groups all have either a positive formal charge next door or some resonance away from the ring in a very strong fashion, and so you see some of the examples of strong withdrawing groups. So the last two groups, moderate and strong withdrawing groups, are meta-directors and greatly deactivate the rate of reaction in the ring. Alright, so let's look at our ortho-para directors. Here's our first two sample reactions. Don't have time to get into open-ended synthesis here, but if you run into a couple of these things that we're going to look at, a few tips and tricks here that'll help you along your way. So first off, we've got toluene. We react in aromatic bromination, and we're going to substitute ortho and para. Well, ortho, there are two ways to get the same product here on either ortho position, and then we're also going to get the para product to that original group. So that weak activator is an ortho-para director, and it will send our group ortho and para. Because we are not very sterically hindered here, our major product is going to be the ortho product, because we're going to discuss groups smaller than a methyl with small electrophiles tend to direct more ortho just because of the numbers game. There's 2 times the odds of getting that. The para is a minor product, but I'll say significant. Okay, so if we need to access that para substituted product, we can through a reaction in a multi-step synthesis. In general, an industry would just separate the two, bottle them both, and sell them both to get their 100% profit on that reaction. We can invoke that para product even though it might be a minor product of this substitution reaction. Well, suppose we take phenol and we have a strong activator, ortho-para director, as we labeled it above, and it's going to send ortho-para. Again, phenol's OH is pretty small there, and so we're going to get ortho and para. So there's our ortho product. We'll draw the para product. To that original directing group. And we'll say here that this is the major product, the ortho product, but less so than our first reaction. Okay, we still have a minor but significant, even more significant para product, because this group, the acetyl group here, is a little bit bigger in the Friedel Crafts acylation, is a little bit bigger than bromine, and so we're going to get a little bit more steric resistance to that ortho position, which is right next door to our original directing group. Okay, what makes both of these reactions relatively good is that if we look at the products of both of these reactions, the products are going to be less reactive they are slower to substitute than the reactants. And why is that? Well, we've just added a weak deactivator and a moderate deactivator to each of these products here. So the carbonyl group's a moderate deactivator, slows down the reaction relative to the reactant. The bromine's a weak deactivator and slows down the reaction. So that enhances monosubstitution. And we get more of the product that we expect. Okay, so we don't have to worry about two groups going on with these reactions. We can control those fairly well. Looking at our meta director here, so any meta director we run into, we do our reaction. Our carbonyl group there is deactivating the ring. It's going to react a little bit slower than benzene, but the meta position, there's only one, because we get one product because both meta positions are going to be the same compound. They're just a 180-degree flip. We don't have to worry about chiral centers of the planar benzene ring there. So we get the same thing. And again, this product has a weak deactivator, and so it is less active than the original. We don't have to worry about multiple substitutions. So that's general directing groups when there's only one group attached. Let's look at some general practices that are going to aid in our synthesis when there are more than two groups attached, or if we run into some special situations. So one thing we can do, and we're going to look at this phenol, this substituted phenol in a moment, but one thing we can do is label our existing groups as weak, moderate, or strong activators and deactivators. Where are they directing to? Do they conflict with each other? And if they do conflict with each other, we're going to notice that the strong activators are going to take priority over the moderate activators, over the weak activators, and in turn over the weak deactivators, over the moderate deactivators, over the strong deactivators. Okay, so a nitro group has less to do with where a direction of a new group goes with a strong deactivator than does an alkyl group. So the alkyl group, being a weak activator, has more control over its direction and so forth. So in the example we see here to the right, if we label these positions that are either activated or deactivated, we keep track of everything. We can nail down where our substituent is going to go. Okay, so if we look, we have conflicting reports here. So this strong activator is activating big time these two positions. The ortho and the para is already occupied by the methyl. The weak activator is a little bitty activator on each of these two. Overall, the strong activator outweighs the methyl. So OH is a strong activator, methyl is a weak. In our chart here, strong activator beats weak activator, and so it directs the product here to form our ortho substitute. And again, both ortho positions are the same because there's a plane of symmetry right there in the molecule, and so we end up getting the bromine ortho to the more active group. You'll notice that we have just a bromine with no catalyst here. And so because this compound is strongly activated, we don't want to use the catalyst, or we could get multiple substitutions because of how active this compound is. We want to try to avoid that. That's one of our exceptions we're going to mention in just a moment. So that's not a mistake. Did that without a FeBr3 catalyst on purpose. One other effect you're going to see that's not exactly obvious is called the ortho effect. And it's kind of a misnomer because it's ortho to one particular spot. And so if you have a meta director competing with an ortho-para director, okay, any meta director competing with any ortho-para, the ortho-para director is going to be more involved with the direction than the meta, except for this one little thing, okay? So the ortho-para controls it, so it's directing ortho and para to itself. Okay, we're labeling that on there. But the ortho effect is that the preferred product, when you do your reaction and you put your group on, it tends to go here to the ortho position of the meta, and the steric hindrance of the directors blocks that ortho position, and then this ortho position is disfavored as the major product in general. So what you tend to see is a product that goes ortho to the meta group. So it's a misnomer, ortho effect, but that tends to be the major product in those situations, this one major product. So it's para to the ortho-para director, but ortho to the meta group there. All right, so nail down using those arguments where your substituent should go. Okay, couple things we got to think about. So what if your see if I can get it where we can see it. There we go. What if your product is more active than the original? So I've done this one before as an experiment in our honors lab to show that this happens. We use mass spec to identify the products. So Friedel Crafts alkylation, there's only primary carbons on this, so no rearrangements possible. We see that ortho tends to be the major product. And you also get some para, because again, methyl is smaller than ethyl here. We'll talk about that in a moment. So we get the major product. But also, you get a couple of byproducts that are visible to a decent degree where you have multiple substitutions. So we have a di-substituted to orthos to paras, have two different peaks, okay, that indicate that these are isomers but the same mass. And then you can have the tri-substituted where a third methyl goes on, or third ethyl goes on. And the reason is you go from having a weak activator to two weak activators, and you've still got some ethyl chloride laying around, and so it's rapidly can add multiple products. So you avoid this if you can. You're still going to get your expected major and minor significant products there, but you will get some more byproducts with these, especially these Friedel Crafts alkylations. We're activating the ring even more. So avoid it if you can, but it's not a huge deal breaker in a synthesis problem on an exam. Now, looking at the ortho-para ratio, we've been talking about it, but sterics, groups larger than an ethyl, like this isopropyl, tend to direct to the para position as the major product. So if we're invoking our sulfonation here, we've got a weak activator. It's an ortho-para director. So these positions are activated, but because it's a bulky group, it tends to direct para over ortho. Ethyl tends to be the 50-50 breaking point, but it also depends on how big your group that you're adding is. A sulfonic acid's a smaller group, and so a little bit bigger than chlorine, but smaller than others, and so it tends to be the alkyl group or the group that's already in place that has the major effect. But you still get some ortho that's minor but significant. So like we've been showing, groups smaller than an ethyl, like toluene here with that methyl group, tend to give us ortho substitution as our major product because of the numbers game. Okay, so we've seen that already. All right, but ethyl tends to be the point. And so you'll get a mixture of products. Both will be significant enough to use in a synthesis. Now, if we have a strong activator, halogenation reactions, if you use a catalyst, you overdo it. So we looked a minute ago, if we want to do monosubstitution, we are going to want to use no catalyst. But if we do, you're going to get multiple substitutions, so you might as well go ahead and use 3 equivalents or an excess of your halogen, because we are ortho-para directing so fast that all 3 can go on in a single reaction. Okay, so avoid the catalyst if you want monochlorination for those. Does not apply to other reactions, okay, just the halogenation reactions. Okay, one other thing that is really important, and you're to be sorely tempted to do this in a lot of reactions, is to use a Friedel Crafts reaction on a moderately or strongly deactivated ring. You cannot do it. It will not work. The literature bears this out. We've tested it in lab directly, again in the honors class, different variations on the theme. This yields no reaction. We have a moderate deactivator here. Friedel Crafts is done, acylation or alkylation. Okay, catalysts that do get that done are in the literature. They're beyond the scope of our course, but the Friedel Crafts is a no-go on deactivated or strongly and moderately deactivated rings. With anilines, another thing we've got to think of is we've got to protect them in protic or Lewis acid. So a Lewis acid, nitrogen's nucleophilic, it adds to the catalyst, and this becomes a strong deactivator. Okay, and so now it is positively charged directly next to the ring, and so it becomes a strongly deactivated system. If anything, it directs meta at this point. Excuse me, if you can get anything to go afterwards, okay? But this is a no-go. This will result in no reaction because you can't Friedel Crafts a deactivated ring. Here you've deactivated it. You could proceed to do something else, but if you're going to do that, you might as well do the following, where you protonate it. Okay, now you've deactivated the ring, and so it's a meta director at this point. If anything, you will nitrate in the meta position. Okay, because you've deactivated the ring by protonating the nitrogen. So we listed NH3 plus as one of our strong deactivators and meta directors. Okay, and if you keep heating it, you might even get a second nitration. So that's NO2 right there, rapidly drawing that NO2. You could get a second nitration as well. Always be careful when nitrating because you're raising the energy of these benzenes. Some of these multiple nitros and deactivated rings become explosive, so you want to be very careful that you know your prep before doing that. So how do you react one of these ortho-para? Because aniline itself is a strong activator. What do? Well, we've got to protect, we've got to react, and then we've got to deprotect. Anytime you use a protecting group, you got to add another step to deprotect in the end. So we protect it as with an acyl halide as an amide, and so we do that. We stick our acyl group on. Even if it's protonated here, we are just adding acid anyway in this step. We've got a moderate activator here. So we play the pH right. We're moderately activating. And then we nitrate. We are ortho-para directing, but we're in a very low water environment. We're not heating, we're not hydrolyzing the amide, and we're bigger than ethyl. So that nitro group goes to the para position for the ortho-para ratio major product. And from there, we want to deprotect, and so we add our aqueous acid, we heat it, we hydrolyze that amide, and at first it gives us the protonated form, but then when we treat it with base in the next step, we get our aniline back, and there we go with our para-substituted aniline. Okay, para-nitroaniline there, and after the deprotection. Okay, and then finally, one last thing we need to see that I see it on the exam. It's not something people normally do, but when you make a diazonium salt and you're preparing to do nucleophilic substitution, you can't use this diazonium as a directing group. You've got to use it immediately and do a substitution. So if you had copper bromide or whatnot, you go ahead, bromide, you go ahead and use your diazonium salt. Don't try to use it as a directing group. Once you make it, you got to use it, and you can't do multiple diazoniums at the same time either. It makes it too unstable.